My name is Bianca Champenois, and I am a second-year graduate student in the SAND Lab. The title of my presentation is a multi-fidelity framework for ocean temperature reconstruction based on model-inferred dynamics and real-time satellite and buoy measurements. This poster highlights some of the research I've done on the development of new techniques to model systems where data from both numerical simulations and sensors are available. I apply the techniques to a temperature model of the Massachusetts and Cape Cod Bay. First off, I'll explain the motivation for this work. Geophysical systems can be modeled with numerical simulations, but these are computationally expensive. Physical sensors can also collect data at future points in time, but these are often scarce or inaccurate. There is a need for modeling tools that combine both sources of data. For my specific example, I have access to 8 years of 3D temperature data from the finite volume community ocean model, a finite volume numerical simulation. However, this data set alone is not useful to estimate the temperature in the future. In contrast, satellites and buoys can also be used to measure ocean temperature, but satellites can only measure temperature at the surface of the ocean, and there are gaps in the data due to cloud coverage. Buoys are more accurate, but they only cover a small number of points in the domain. The framework I developed can be used to model full 3D fields of quantities of interest using a combination of physical sensors and numerical simulations. It consists of 4 steps. First, I apply principal component analysis to the data from the finite volume simulation to reduce the dimensionality of the data. I only keep the first 2 modes as they are sufficient to retain the patterns in the data. The PCA coefficients vary with time and can be projected onto the eigenvectors to reconstruct the full vertical temperature field at each xy point. Second, I build a neural network that can predict the PCA coefficients as a function of surface temperature. I also build a second neural network to predict the standard deviation of the predictions. The neural networks take the surface temperature of the point of interest and nearby points as input. They can be used to predict PCA coefficients at future times when new data becomes available. Third, I use the neural network to predict the PCA coefficients for the real-world satellite surface temperature data. I project these PCA coefficients onto the eigenvectors to reconstruct the full 3D field, which gives me a real-time estimate for ocean temperature. And finally, I combine this 3D temperature field with data from in-situ buoys to build a multi-fidelity Gaussian process regression model that is more accurate than using data from just the simulation or sensors alone. The final model predicts both the mean and the variance. The variance can be used for optimal sampling, path planning, and extreme event prediction. The model can also be augmented to include new sources of data that may become available. I hope to implement this framework into the CGLASS online tool for other people to use and access the model.